Hi, it's Mrs. Golding, and we are looking at Friday paper 29. We're going to do problems 4, 5, 7, and 11 today. So we're going to start with number 4, where we are finding the quotient of two decimals. So we're going to go ahead and approach this problem using the standard algorithm. A lot of times I've used the box method. Same concept, just a different method. So we're going to put, we have the quotient, we have the dividend, and we have the divisor. The dividend is inside. The divisor goes on the outside. And remember, the divisor must be not must be, I should say, but in the standard algorithm, it's best if it's a whole number. Here we go. Change that. 3 6/10. So when you are changing the, you're moving that decimal, what you're really doing is you're multiplying that divisor by a factor of 10. So you just made 3.636 by multiplying by 10. So in order to keep that ratio equivalent, you're going to have to do that to the dividend also. All right. So then we're going to move that decimal, and then you're going to raise the roof, pop it right up where it belongs, and then we're going to start the division process. And the hard thing about this problem is you have a 2-digit divisor instead of just a 1-digit divisor. And the first 2 digits in your dividend are smaller than those. So that means you're going to have to look to the third one. So whenever I have that, then I want to round, and I want to make a guess because I don't know any facts like 36 times something. I don't have those facts memorized, but I'm going to use what I do know. So 36 is pretty close to 40, right? And 283, so these three numbers, that's pretty close to 280, right? So I know 40 and 280. Now, I might not have that fact memorized, but what about just 4 and 28? So if I'm dividing 28 by 4, it makes me think, okay, I'm going to reverse that to 4 times what gives me 28, and I get 7. So that gives me a starting place, right? So I'm going to try it. Let's put a 7 here. 7 times 6 is 42. And 7 times 3 is 21, plus 4 is 25. And then let's make sure we're good. Don't do that. 1, 3. Now, if that remainder had been greater than 36 or even equal to 36, that means that I would need to bump up my quotient by 1, but I'm good. So I'm going to now, I have a remainder of 31, so I'm going to bring down the 4. So we're going to do the same thing. 36 goes into 314. And so if I round that to 40 again, and then that's really close to, I could say 32. That's going to be an overestimate, right? Or 300 is going to be an underestimate. So let's make an overestimate. And we use a 4 and a 32. My overestimate is going to be 8. So let's try it and see what happens. That's how we do this in math, right? 8 times 6 is 48. 24, 29, 28, 24, 28. We're going to look here. So 288, 6, 2, 2, 26. Okay, so I have a remainder of 26. So what am I going to do with that remainder? Could I make this 7 8/10 and 26 36? Can't do that, right? You can't combine. Once you've settled on a decimal up here, we got to continue. So we can annex a 0. You remember what that means. Annex a 0, bring it down. And I know that 36 times 8 is 288, and that's too big, right? So I could try 7. And so 36 times 7, 21, 25. Now, where did I do that already? Right up here, right? That's how I got my 7. So let's go 7, 252. And when I subtract, I get 8. Now we're really close. That's a much smaller remainder, but I still need to come out as perfect as possible. So annex another 0. 36 goes into 80 how many times? Well, 40 times 2 is 80, so I'm going to guess it's a 2, right? So 6 times 2 is 12, and 672. So 80 minus 72, what is that going to give you? 8. Now, what do you notice? Isn't that the same thing I was working with before? I can annex another 0, but what's going to happen? It's going to be a repeating decimal, right? So the only thing that's going to repeat is that 2. So my repeating bar, which funny enough is also called a vinculum, is going to just go over the 2. So when you write this into TeacherMade, when you're putting this in on Canvas, you're going to write 7.872, and then you're going to add what's called an ellipsis, like that. And that means and so on, and so on. It's not completely the right thing to write for this, but we don't have a repeating symbol for that particular assignment. So let's go to number 5. So it says choose all of the values that represent solutions to this equation. So some number squared, n squared equals 43. So when I look at a problem like this and it doesn't really make sense to me, I'm going to rewrite it in a way like with a problem that does make sense. So what if it said n squared equals 16? So in my mind, that makes more sense. Some number squared equals 16. What could that number be? Well, the way we've been talking about that is the square root. And it's been a minute since we've had our section where we really focused on square roots. But you'll remember when you take the square root of a number, we've been talking in positive values most recently because we've talked about like distance or measurement when we're talking about Pythagorean theorem, and you can't have a negative value for that. So, but the truth of the matter is that the square root of 16 is plus or minus 4, right? And so remember that symbol, plus or minus 4. So I'm going to kind of take this knowledge and go back to the question that's being asked. So in this case, we've got this some number squared equals 43. Well, is 43 a perfect square? No, it's not. And I'm going to write it right here. Same way, so right, same pattern. I'm going to do the same concept I did with 16. So n would be plus or minus square root of 43 if I leave it in what's called radical form. And so if we look over here in our answers, right, is there anything that looks like the square root, the positive square root of 43? Yep, that's going to be this guy right here. And then where would I find the negative square root of 43? It's right here. Okay. A lot of times we forget that value, but it has 2 values. The rest of these are all different, aren't they? So negative 43 squared, that's 43. Negative 43 times negative 43, whatever that is. Probably a little bit more than 1,600, wouldn't you say? Yep. So half of 43 is not going to do it. And this one right here is probably the biggest distractor of all of them. And when you're taking iLearn, you're going to look for those distractors. It's like what they think you might want to say, because a lot of times when we talk about square roots, you want to think of it in terms of half of a number. Like the square root of 16, you might say is 8 because you want to cut it in half, but that's not what we're doing, is it? Okay, let's go to number 6. Nope, Number 7. Okay, so this says choose all tables that represent a linear function. Okay, so there's 2 issues here. Is it linear and is it a function? So you'll remember when we talked about functions and we had graphs and we had tables and we had equations, and we said, is it a function? And remember, when we go back in our brains to elementary school where your teacher built those cool function machines, and they said you put something in and then you have a rule like +2 or whatever, and then you get something out. So sitting on the carpet and you're doing those function machines, and you guys were the best at it, right? So to be a function, when you put something in and you get something out, you can't put that same thing in and get a different thing out. That's not the way the function machine works. Okay, that would be a broken Dr. Seussical function machine. So we know that we can't have any repeating x values. So let's just kind of glance over our tables. So we have, and I'm just going to kind of color code them. These are my x values, right? Here. I know this is kind of smushed together. It was just done quickly on a spreadsheet, and so it's not very nice. So these red ones are my y values. The yellow ones are my x values, right? Do any of those x values in those tables repeat within the same table? And when I say within the same table, I'm just going to make this easier for you to see. Table A is this. Table B is this, and so on, okay? So just imagine there's 1, 2, 3, 4, 5, 6 different tables here. Okay, so far so good. Now, the other thing is when you're looking at a function, you remember the vertical line test. So if I had a graph and it looked like this, right? So we have this parabolic shape, but it's opened up like that, like a C. That is not a function, because look, if I were to draw my vertical line and I'm going to carry it all the way across like this, see, it crosses here and here and here and here, so that shares those same x values at those points. So it's not a function. That's not linear either, is it? Okay, so let's now look for one of the other key factors of a linear relationship is that it will have a constant, I'm going to write it down here like this, constant rate of change. And remember, rate of change is just code for slope. So change in y, remember delta y, delta x. Change in y over change in x is equal to my m, which is my slope. So then let's figure out change by adding or subtracting, right? Normally we kind of talk about it in subtraction, but from on table A, from 1 to 2, add 1, 2 to 3, add 1, 3 to 4, add 1, and I can write that out here, right? And then every time those increase by 1, what's happening to my y? 1 plus 2 is 3. 1, 3 minus 2 is 1, and then 1 plus 2 is 3. So I didn't have a constant rate of change, did I? It went up, then it went down, and so this would have been 2 over 1, and this would have been negative 2 over 1. So this is not a possibility. Table A. So table B, 9, 8, 7, 6. Each time we're going down by 1. And then 8 to negative 4, we're going up 4. 4 to negative 2, what are we doing? Up 2. 2 to 1, negative 1, we're going up 1. So this does not have a constant rate of change, right? So cross him out. Now let's look at C. Negative 2 to negative 1, plus 1. Negative 1 to 0, plus 1, plus 1. So far, those are all plus 1. what's 1 to 2, 2 to 3, 3 to 4? Those are all plus 1. So the rate of change would be 1 over 1, meaning it has a slope of 1, right? And what's the y-intercept, by the way, on here, right? It's when x equals 0, and we have it on our table. When x equals 0, y equals 3. So this I could rewrite as y equals 1x, or just x, plus 3, right? The y-intercept. So C is definitely a linear function. Okay, let's go to D. 2, 3, 4, 5. Those are all plus 1. 1, 2, plus 1. 2, 4, plus 2, plus 1. See how that's not constant? So we're going to exit that one out. Let's do E. 2, 3, 4, 5. Those are plus 1. 1, 2, 3, 4, plus 1, right? And so we have a slope of 1 here, and it is a constant rate of change. So we're going to select E. Let's look at the next one. 0 to negative 4. We minus 4, minus 4, minus 4. 1 plus 2 is 3. 3 plus 2 is 5. 5 plus 2 is 7. So I have plus 2. So my slope is 2 over negative 4, which becomes negative 1 half, right? There's a constant rate of change. It's negative, right? So my graph is going to have a orientation like that, right? So this is a linear function, okay? Pretty complicated one. Last question. Write the following in scientific notation. I tell you what, I'm going to do A for you, but then you have to do B, okay? So for this one, we have a decimal point that's very small. I don't even know if I could say it. It's so small, right? And when you're talking about decimals that small, you're talking about like the diameter of an atom, right? Or the diameter of the nucleus of an atom even, right? So tiny numbers. And when you have these giant numbers, like in number B, this is humongous, right? That's like the distance from here to Jupiter. I don't really know what the distance from here to Jupiter is. Maybe you can look that up. But tiny number, big number, right? When you have a really tiny number and you're going to express that in scientific notation, do you remember what is going to end up? You're going to end up with, is it going to be times 10 to a positive exponent or a negative exponent? It's going to be a negative exponent, because remember, when you have like 3 to the negative second power, that's like 1 over 3 squared, right? And so instead of, when you make it times 10 to a negative power, instead of multiplying by 10, a power of 10, you're dividing by a power of 10. Because see how it's really becoming like a fraction, which is division, right? So we got to figure out what we're going to use as our first number. And so we got to find a number between 1 and 10. So nope, 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 yep. How many times did I move that decimal over to get there? 1, 2, 3, 4, 5. That's going to be my negative 5 power, right? And then I'm going to rewrite 6.5708 times 10 to the negative 5th power. When you are putting that into Canvas, you're going to only need to insert this number and I believe this number. You might see times 10 and it'll have a little caret. And then so you're just putting in those two numbers. Okay, you're going to do the same thing with B, only this time you remember when the decimal's out of sight, it's on the right. So you're going to move in the direction left to make a number between 1 and 10. And remember your significant digits. None of these zeros are considered significant when you're moving that decimal over. So you need to focus on that. Okie doke. Well, remember, you are important and the world needs you, and so do I. Have a good day.